Hi, my name is Ali Ayub, and I'll be presenting our paper, Few-Shot Incremental Object Learning by a Robot, that is accepted at IEEE IROS 2020. So deep learning systems have achieved remarkable success in object classification or object detection. However, they require all the training data to be available in a single batch. Humans, on the other hand, actually learn incrementally, in which they learn new object classes while remembering the previous object classes. And this is the process that we call incremental learning, where the model is required to learn new data incrementally while remembering the previous data that it learned in the previous increments. So humans also require a very small amount of training examples per object. The current deep learning system, however, require a large amount of training examples per class. Now, for real-world robotics applications, robots will only have a small amount of training examples. That means they were required to learn new objects from only a small amount of examples, which is the field that we call few-shot learning. So in this paper, we actually deal with a combination of these problems, which is few-shot incremental learning, in which the robot is required to learn objects from only a small amount of training examples provided by a human in an incremental fashion. This process obviously has a lot of real-world applications, like for household robots that might require object cleaning tasks, which will have to be updated over time based upon the owner of the robot and where they are in a particular house. And also for industrial robots, like packaging robots, which need to update their database incrementally. Now, incremental learning on neural networks runs into a problem called catastrophic forgetting, in which if a model learns only using the new class data, it forgets the old classes and the overall accuracy decreases. Now, to deal with this, a lot of computer vision approaches have been proposed that store the images of the old classes while learning new classes. However, that run into a lot of issues. So first, it requires a large amount of memory, which might not be the case for robots which have a limited onboard memory. It also leads to privacy and security issues for saving real images of the old classes. And in particular, all these neural network-based approaches actually require a large amount of training examples per class, which probably is not the case in real-world robotics applications where they only have a few training examples per class available. Now, there have been some approaches proposed for robotics applications. However, many of them still require the old class data to be available. Some don't really test on a real robot, and there are further issues with a lot of these robotics application-based approaches. So first, all of these approaches actually have not been tested on benchmark datasets or compared against other computer vision-based approaches, so we don't really know how good they are. Next, that is a bigger issue, which is actually all these approaches use training data as test data as well, which means they use same objects as training set and same objects in the test set, which obviously is not the case in real-world applications. And lastly, all of these approaches have been tested on a very small set of classes, which actually does not lead to catastrophic forgetting, and it might not be the best way to test for incremental learning. So in this paper, we actually use our previously proposed approach called CBCL, Centroid-Based Concept Learning, which actually has been shown to produce state-of-the-art results on benchmark datasets, and it can learn with only a few training examples per class. So in this case, in our overall system, the robot is required to learn object classes by the objects presented by a human with the labels, and then eventually required to clean the particular objects required by the human, and also learn some semantic object arrangement modules. So I'll explain them in the next slides. So the CBCL approach actually uses the process of agar clustering, in which for a new image class, it actually extracts the feature vectors for the images of the new class using a pre-trained feature extractor, and then it initializes a centroid for the new class using the first image, and then for the next images finds the Euclidean distance of the new images to the previously learned centroids for that class. And if the new image is actually closer to a centroid, which means below a predefined distance threshold, then the centroid is updated using the new images feature vector. Otherwise, a new centroid is created for that class using the new images feature vector. And in this way, the model actually creates a different number of centroids for different classes using a single hyperparameter, the distance threshold, which is supposed to cover the different views or layouts of the objects learned by the robot. So in the test phase, CBCL finds the feature vector of the test image and then compares it against all the centroids learned by agware clustering. And then using the n closest centroid, which is the hyperparameter n, and using the n closest centroids, it actually finds the prediction weight of different classes based upon the distance of those centroids from the test image and the classes that they belong to. And these prediction weights are then multiplied by the inverse of the training images of a particular class to deal with class imbalance. And eventually, the prediction label for the test image is based upon the class with the highest prediction weight. So for the table cleaning task, there will obviously be a clutter of objects present on a table in front of the robot. So the robot obviously has to localize them. And for localization, we use a RetinaNet, which is pre-trained on COCO dataset. But we obviously only use the bounding boxes of the objects and then crop those bounding boxes to get the images for CBCL to classify. Now, as I said in the previous slide, that the robot would have a lot of objects present in front of it. So for the table clean task, it gets the locations of those objects from the localization module, and then the labels of those objects by passing the cropped bounding boxes through CBCL, and then eventually it cleans or moves the objects from the table based upon a label provided by a human. So the last part of our system is the semantic object arrangements module, in which the robot is required to learn different arrangements of objects using only a single training example. Like shampoo, toothbrush, or toothpaste belong to things in bathroom, and uh, the robot actually uses the localization module and the CBCL module for finding the labels and the location of the objects in the arrangement in the training set, and then creates a centroid using those values, which is different from the centroids generated for CBCL. And during the test phase, then it can actually predict different objects that are missing from a particular arrangement or wrong objects in a particular arrangement. So for testing, we bought 22 different object classes with 15 objects per class. And for the incremental learning phase, we showed 2 poses of each object, which means 30 images per class. For the few shot incremental learning case, we used 5 or 10 training images per class for training, and the rest were used as test images. And you can see these images were realistic with imperfect background, imperfect lighting conditions, and some transparent objects, and some with very small size. So we use the Keras deep learning framework and NVIDIA 1070 for training. Resonant 50 pre-trained on ImageNet was used as a feature extractor, and the parameters, hyperparameters for CBCL were tuned using cross-validation. So for few-shot incremental learning experiment, we compare against few-shot learning baseline and fine-tuning, which uses a ResNet 50 feature extractor, and then a linear layer trained on cross-entropy loss. Few-shot learning baseline is not designed for incremental learning, so it uses old and new class data. Essentially, it is a upper bound for our experiment. And the fine-tuning doesn't use any of the old class data, and it only uses new class data. For this experiment, we run on 5-shot and 10-shot incremental learning experiments, and we run 10 runs of each experiment and then average the results for robustness reasons. So here are the results for our experiment, in which we have 5-shot incremental learning with 1 class per increment as A, 10-shot incremental learning, 1 class per increment as B, and then 5-shot, 2 classes per increment, and then 10-shot, 2 classes per increment. And as you can see, our approach produces very similar results to few-shot learning baseline, and fine-tuning suffers from catastrophic vetting. Also, you should notice that few-shot learning baseline actually uses all the data, while our approach only uses the new class data. Also, for 5-shot experiment with 1 class per increment, our approach produces very similar results to few-shot learning baseline, which means CBCL is best suited for situations with limited data. And the learning time for this experiment was 13 seconds, and the prediction time was on average 11 seconds. Um, so for table cleaning experiment, we trained CBCL on 5-shot incremental learning with 2 classifier increment. And for this experiment, there were always 6 objects present on a table, with 2 from a specified class. The Baxter robot, designed by Rethink Robotics, was used for the experiment, and the object classes were specified using a keyboard by the experimenter. And we ran 10 runs of the experiment again, with different objects to be cleaned for robust runs. So in the 10 runs of this experiment, we encountered 3 different kind of errors. One is detection error, in which the localization module is unable to detect the objects, a classification error, and the movement error, in which the robot is unable to move the object. So there was no movement error because we used the suction gripper to move the object, and it was perfect. Classification error was a little similar to the few-shot learning experiment, and the detection error was the highest. Um, Overall, the total time for the whole process was only 51 seconds, so it seems like it can be applicable in real-world situations. So for our last experiment, we tested the semantic object arrangements module, and for this experiment, we used 5 different arrangements that were learned by the robot by a single example with 3 objects per arrangement. For this purpose, we actually designed a feature vector to save the training arrangements. So feature vector had it was a binary kind of vector, initialized with zeros, which had 22 places for object labels, um, then 22 by 22 matrix flattened for the location of the object above or below than the other object, and then another one for right or left. So the overall size of the feature vector was 990 by 1. And for a particular semantic arrangement, then we replace zeros by ones at the locations for the labels and the locations of the objects. So for the test case, we had 20 different arrangements, 10 with which had a missing object, which means it only had 2 objects, and 10 with a wrong object, which means it had 3 objects, but one was a wrong object from the arrangement. Um, and for all these test arrangements, all the objects were different from the training objects that were used in the training set. The CBCL module for classification was trained using 5-shot incremental learning with 2 classes per increment. And out of those 20 cases, there were 9 cases when the model has to make 2 predictions and 11 with only 1 prediction. Now the cases with 2 predictions were there because there were times when the model would make a wrong prediction about one of the objects using the classification module, or the localization module would just not detect one of the objects in the test arrangement, which means then that would be considered as a wrong or a missing object for the model itself, so that it had to make 2 predictions. So the 1 prediction case, our model achieved 100% accuracy. For the 2 prediction case, the R model achieves 56% accuracy because for the 2 predictions case, it only has 1 object to make a prediction about 2 others based upon arrangements, and that 1 object could be present in 2 different arrangements, and then it would just have to make a random guess. So the overall accuracy then was 80%. So to summarize, we presented the few-shot incremental object learning application on a robot, specifically for cases when the training and test images were different, and the model had to learn a large number of classes, which has not been done before. And we also presented realistic applications like table cleaning task, and then eventually the semantic object arrangement learning module. Um, we had some limitations in our work. For example, we only used a tabletop environment and only used 5 different object arrangements. Um, uh, but despite of those limitations, which we will try to remove in our future work, our paper contributed in different ways. Particularly, we presented a realistic approach for dynamic learning of task-specific objects. Um, and then our approach for few-shot incremental object learning can be used by non-expert humans to teach the robot. And lastly, we provide benchmark evaluations on a data set that we captured ourselves, and we will make it available so that these benchmark evaluations can then be used by future works that want to compare against our approach on the given data set. Thank you. And if you have any questions, just let me know with which whatever tool they're using now in this situation.